Understanding Physics, 3 volumes in 1, by Isaac Asimov. Read, recorded, and produced by JohnLothe. Chapter 10. Gases. Density. The properties of liquids described in the previous chapter are important in connection with a fundamental question concerning the ultimate composition of matter, a question that was of great interest to scientists as long ago as the time of the ancient Greeks. Matter can be subdivided indefinitely, as far as the eye can see. A piece of paper can be torn in half, in quarters, and in eighths, and still remain paper. A drop of water can be divided into 2 smaller drops, or into 4 still smaller drops, and still remain water. Can such a subdividing process be continued forever? Is matter continuous even to ultimate smallness? There was no way in which the ancient thinkers could test this in actual practice, and they resorted to logical arguments based on what they considered first principles. Some, notably Democritus of Abdera, 5th century BC, maintained that matter could not be subdivided forever, but that eventually a small portion was reached that could not possibly be broken down further. This he called atomos, meaning uncuttable, and we now speak of his views as representing atomism, or an atomic theory. Other Greek philosophers, notably Aristotle, argued against this notion. However, adducing reasons that made the idea of atoms seem illogical. Other Greek philosophers, notably Aristotle, argued against this notion, however, adducing reasons that made the idea of atoms seem illogical. By and large, the non-atomistic view won out and remained the prevalent belief of scientists for 2,000 years. If one confined oneself to the study of the properties of solids, one could scarcely help but be sympathetic to the Aristotelian view. For there is nothing about a solid that would make it seem logical to consider it to be composed of a conglomeration of small particles. If it were, we would have to suppose the particles to be stuck firmly together, since solids acted all in one piece. And if we are going to suppose that particles are stuck firmly together, why not discard the particles altogether and suppose the solid to be all one piece of continuous matter in the first place? Where solids are concerned, the situation is quite different. By the very fact that liquids do not move all in one piece, it might reasonably be suggested that they are composed of separate particles. A mass of tiny metal spheres or a heap of powder would take on the overall shape of any container in which they were placed, and they would pour as a fluid would. If the particles were rather sticky, they would pour like a viscous fluid. In fact, many of the properties of liquids could be explained nicely by supposing them to consist of submicroscopic particles which attract each other somewhat. Surface tension could be explained in this fashion, for instance. However, all the properties that make liquids suggest atomism more effectively than solids do are further intensified in gases. And in actual fact, it was the study of gases through the 17th and 18th centuries that finally forced scientists to reverse the early decision in Aristotle's favor and to take up again, at the start of the 19th century, the long-discarded view of Democritus. Gases differ from liquids most clearly and obviously, perhaps with respect to density. In comparison with liquids, gases are thin and rarefied. The density of water is 62.43 pounds per cubic foot in the English system. Using metric units, it is 1 gram per cubic centimeter in the CGS system, and 1,000 kilograms per cubic meter in the MKS system. The least dense liquid at room temperature or below is liquid hydrogen, while the densest is mercury. The former has a density of 0.07 grams per cubic centimeter. The latter, a density of 13.546 grams per cubic centimeter. At elevated temperatures, some metals, such as platinum, would melt to liquids with densities as high as 20 grams per cubic centimeter. The density of solids falls, for the most part, within this range, too. The lightest solid, solid hydrogen, has a density of 0.08 grams per cubic centimeter, while the heaviest, the metal osmium, has one of 22.48 grams per cubic centimeter. Such densities can be expressed in allied fashion as specific gravity, a term dating back to the Middle Ages. Specific gravity may be defined as the ratio of the density of a substance to the density of water. In other words, if the density of mercury is 13.546 grams per cubic centimeter, and that of water is 1 gram per cubic centimeter, then the specific gravity of mercury is 13.546 grams per cubic centimeter divided by 1 gram per cubic centimeter, or 13.546. Because the density of water is 1 gram per cubic centimeter, the specific gravity comes out numerically equal to the density in the CGS system. But you must not be misled by this apparent equality, for there is an important difference in the matter of units. In dividing a density by a density, the units, grams per cubic centimeter, in this case cited in the previous paragraph, cancel, so that the figure for specific gravity is a dimensionless number. The units cancel when specific gravity is calculated, no matter what system of units is used for the densities. In the MKS system, the densities of mercury and water are, respectively, 13.546 per cubic meter and 1,000 kilograms per cubic meter, or respectively 13,546 kilograms per cubic meter and 1,000 kilograms per cubic meter. By taking the ratio, the specific gravity of mercury is 13.546, as before. In the English system of units, the densities of mercury and water are 845.67 pounds per cubic foot and 62.43 pounds per cubic foot, and the ratio is still 13.546. The convenience of a dimensionless number is just this, then. It is valid for any system of units. The specific gravity of gases is much less than that of either liquids or solids. The most common gas, air, has a specific gravity of 0.0013 under ordinary conditions. The lightest gas, hydrogen, has, under ordinary conditions, a specific gravity of 0.00009. An example of a very dense gas is the substance uranium hexafluoride, which is a liquid at ordinary temperatures, but if heated gently, is converted into a gas with a specific gravity of 0.031. Thus, under ordinary conditions, even the densest gases are less than half as dense as even the least dense liquids or solids, while a common gas such as air has only about 1/700th the density of a common liquid such as water, and only about 1/2000th the density of common solids, such as the typical rocks that make up the Earth's crust. Gases share the fluid properties of liquids, but in an attenuated form, as is to be expected, considering the differences in density. For instance, gases exhibit pressure as well as liquids do, but gas pressure is considerably smaller for a given height of fluid. A column of air a meter high will produce a pressure at the bottom only 1/700th that of a column of water a meter high. Nevertheless, we live at the bottom of an ocean of air many miles high. Its pressure should be considerable, and it is. It is equivalent to the pressure produced by a column of water 10 meters high. This pressure was first measured by the Italian physicist Evangelista Torricelli, 1608 to 1647, in 1644. Torricelli took a long tube, closed at one end, and filled it with mercury. He then upended it in a dish of mercury, The mercury in the tube poured out of the tube, of course, in response to the downward pull of gravitational force. There was a counterforce, however, in the form of the pressure of the atmosphere against the mercury surface in the dish. This pressure was transmitted in all directions within the body of the mercury. Pascal's principle, see page 119, including a pressure upward into the tube of mercury. As the mercury poured out of the tube, the mass of the column, and therefore the gravitational pull upon it, decreased until it merely equaled the force of the upward pressure due to the atmosphere. At that point of balancing forces, the mercury no longer moved. The mercury column that remained exerted a pressure due to its own weight that was equal to the pressure of the atmosphere due to its weight. The total weight of the atmosphere is, of course, many millions of times as large as the total weight of the mercury, but we are here concerned with pressure, which, be it remembered, is weight or force per unit area. It turns out that the pressure of the atmosphere at sea level is equal to that of a column of mercury just about 30 inches, or 76 centimeters high. Torricelli had, in effect, invented the barometer. Air pressure is frequently measured, particularly by meteorologists, as so many inches of mercury or centimeters of mercury, usually abbreviated in Hg or cm(Hg) respectively. It is natural to set 30 inches Hg or 76 centimeters Hg equal to 1 atmosphere. A millimeter of mercury, mmHg, has been defined as 1 torricelli, in honor of the physicist. So 1 atmosphere is equal to 760 torricellis. Air pressure may also be measured as weight per area. In that case, normal air pressure at sea level is 14.7 pounds of weight per square inch, or 1,033 grams of weight per square centimeter. In that case, normal air pressure at sea level is 14.7 pounds of weight per square inch, or 1,033 grams of weight per square centimeter. Expressed in the more formal units of force per area, 1 atmosphere is equal to 1,013,300 dynes per square centimeter. 1,000,000 dynes per square centimeter has been set equal to 1 bar, for a Greek word for heavy. So 1 atmosphere is equal to 1.0133 bars. Naturally, if it is the pressure of the atmosphere that balances the pressure of the mercury column, then when anyone carrying a barometer ascends a mountain, the height of the column of mercury should decrease. As one ascends, at least part of the atmosphere is below, and what remains above is less and less. The weight of what remains above, and therefore its pressure, is lower, and so is the pressure of the mercury it will balance. This was checked in actual practice by Pascal in 1658. He sent his brother-in-law up a neighboring elevation, barometer in hand. At a height of a kilometer, the height of the mercury column had dropped by 10%, from 76 centimeters to 68 centimeters. Furthermore, the atmosphere is not evenly distributed about the Earth. There is an unevenness in temperature that sets up air movements that result in the piling up of atmosphere in one place at the expense of another. The barometer reading at sea level can easily be as high as 31 inches Hg or as low as 29 inches Hg. In the center of hurricanes, it may be as low as 27 inches Hg. These highs and lows generally travel from west to east, and their movements can be used to foretell weather. The coming of a high, a rising barometer, usually bespeaks fair weather, while the coming of a low, a falling barometer, promises storms. For all that air pressure is sizable in quantity, the value, 14.7 pounds of weight per square inch, is most easily visualized by a person used to the common measurements in the United States. It goes unnoticed by us. For thousands of years, men considered air to be weightless. We still say as light as air, or an airy nothing. The reason for this is that air exerts its pressure in all directions. as all fluids do. An empty balloon, although supporting the full pressure of miles of air, will rest with its mouth open and its walls not touching, for the air within it has an outward pressure equal to the inward pressure of the air outside. Place the balloon in your mouth, however, and suck out the air within so that the inward push of the air outside is no longer balanced. Now, the walls of the balloon will be pushed hard together. The same factors apply to human beings. The air in our lungs, the blood in our veins, the fluid in our bodies, and living tissue is essentially a thick viscous fluid, is generally at air pressure and delivers a pressure outward equal to that of the atmosphere inward. The net pressure exerted on us is zero, and we are therefore unaware of the weight of the air. If we submerged ourselves in water, the pressure from without rapidly increases, and it cannot be matched by pressure from within without damage to our tissues. It is for this reason that an unprotected man, such as a skin diver, is severely limited in the depth to which he can penetrate, regardless of how well equipped with oxygen he may be. On the other hand, forms of life adapted to the deeps exist at the extremest abyss of the ocean, where the water pressure is over 1,000 atmospheres. Those life forms are as unaware of the pressure, balanced as it is from within, and as unhampered by it as we are by air pressure. Once it was recognized that air had weight and produced a pressure, it was also quickly recognized that this could easily be demonstrated, provided it were not balanced by an equal pressure from within. In other words, it seemed desirable to be able to remove the air from within a container, producing a vacuum, a Latin word meaning empty, so that the air pressure from without would remain unbalanced by any appreciable pressure from within. Torricelli had formed the first man-made vacuum, inadvertently, when he had upended his tube of mercury. The column of mercury, as it poured out, left behind a volume of nothingness, except for thin wisps of mercury vapor, and this is still called a Torricellian vacuum. Just a few years later, in 1650, the German physicist Otto von Guericke, 1602 to 1686, invented a mechanical device that little by little sucked air out of a container. This enabled him to form a vacuum at will and to demonstrate the effects of an unbalanced air pressure. Such air pressure would hold two metal hemispheres together against the determined efforts of two 8-horse teams of horses, whipped into straining in opposite directions to pull them apart. When the air was allowed to enter the hemispheres once more, they fell apart of their own weight. Again, air pressure gradually forced a piston into a cylinder being evacuated, even though 50 men pulled at a rope in a vain attempt to keep the piston from entering. In other respects, too, a gas, like air, has fluid properties in an attenuated form. It exhibits buoyancy, for instance. We ourselves displace a volume of air equal to our own volume, and the effect is to cause a 150-pound man to weigh some 3 ounces less than he would in a vacuum. This is not enough to notice ordinarily, of course, but for objects of very low densities, the effect is very noticeable. This is particularly true for substances such as certain gases that are lighter than air. Hydrogen gas, for instance, has only 1/14 the density of air. In consequence, hydrogen, penned within a container, is subjected to an upward force like that of wood submerged in water. See page 124. If the container is light enough, it will be carried upward by the upward force. If enough hydrogen is involved, the force will be sufficient to also carry upward a suspended gondola containing instruments or even men. The first such balloons were launched in France in 1783. When there is relative motion between a solid and a gas, there is friction, as there is between a solid and a liquid. though again the effect is much smaller, where a gas rather than a liquid is involved. The friction with gas, air resistance, is enough, however, to slow the velocity of projectiles to the point where it must be allowed for if an artilleryman is to aim correctly. Air resistance also prevents a complete and perfect interchange of kinetic and potential energy by dissipating some of the energy as heat. See page 97. The downward force of the gravitational field is proportional to the total mass of the body, while the upward force of air resistance is proportional to the area of contact of the moving body with air in the direction of its motion. For compact and relatively heavy bodies, such as stones, bricks, and lumps of metal, the gravitational force is high, while the contact with air is over a relatively limited area, so that air resistance is low. In such cases, motion is close enough to what it would be in a vacuum, for Galileo to have been able to draw correct conclusions from his experiments. For light bodies, the gravitational force is relatively low. If such bodies are also thin and flat, as leaves or feathers are, for instance, they present a relatively large area to the air, and air resistance is relatively high. In such cases, air resistance almost balances the gravitational force, and these light bodies therefore fall slowly. They would fall quickly in a vacuum. This slow rate of fall fooled the ancient Greek observers into believing there was an intrinsic connection between weight and the rate of free fall. There is a terminal velocity reached in motion through air under the influence of a constant force, such as gravity, since air resistance does not remain constant but increases with the velocity of an object through air. As velocity increases, air resistance eventually balances the gravitational force. For heavy, compact objects, this terminal velocity is very high, but for light, flat objects, it is quite low. Snowflakes quickly reach their low terminal velocity and accelerate no further, though they fall for miles. If a compact object is suspended from a light, flat one, the two objects together reach a far lower terminal velocity than the compact object would by itself, and this is why a parachute makes it possible to fall safely from great heights. Again, there is a Bernoulli effect for gases as well as for liquids, and air pressure drops as the velocity of moving air increases. A jet of air moving across an orifice covers that orifice with a low-pressure area, or a partial vacuum. If a tube connected with the orifice dips into a liquid under normal atmospheric pressure, that liquid is pushed up the tube and is blown out in a fine spray. When a baseball or a golf ball spins in the air, one side spins with the motion of the air flowing past the ball as it moves. The other side spins against the motion. The side that spins against the motion has a greater velocity relative to the air, and the air pressure is less in that direction. The ball is pushed in the direction of lower pressure, so that the baseball curves in its flight, usually desirable if it is the pitcher throwing the ball, while the golf ball hooks or slices, usually undesirable. Where high velocity through air must be maintained with a minimum of force, streamlining is important. This importance increases with velocity, since air resistance also does. Thus, a horse and wagon need display no streamlining, and automobiles need display very little. A trend toward extreme automobile streamlining, initiated in the late 1930s, was a matter of appearance rather than necessity and was abandoned. Airplanes, however, must be streamlined, and in reaching supersonic speeds, it was not so much higher power that had to be developed, but the proper design for minimizing air resistance. Furthermore, airplane wings, themselves streamlined, are so designed that the air must move over a greater distance above than below, and so must move more rapidly above than below. This, by Bernoulli's principle, means there is less pressure above than below, and therefore a net upward force, lift, that helps support the plane. Boyle's Law. The properties of gases are of crucial importance with respect to the possibly atomic nature of matter. If matter is non-atomic, then variations in density must be caused by the intrinsic differences in the density of matter itself. Every bit of it, however small, must be as dense as every other bit. There would be no holes or empty space in matter, as there would be if the matter consisted of atoms. If matter consisted of atoms, there might be space between the atoms, a space containing only vacuum. Matter might be made less dense, then, by pulling the atoms apart in some fashion, so as to increase the proportion of empty space within a given volume. Conversely, matter might be made more dense by pushing the atoms together to reduce the proportion of empty space. Indeed, it might seem that the density of a particular substance could be changed in just this fashion by heating or cooling. Density usually decreases with heating and increases with cooling. Thus, although the density of cold water is 1 gram per cubic centimeter, that of hot water is only about 0.96 grams per cubic centimeter. Then again, solids melt to liquids if heated sufficiently, and the liquids become solids again if cooled. This change in the state of matter is accompanied by a sudden change in density. Thus, ice has a density of 0.92 grams per cubic centimeter, but as soon as it is melted to water, the density increases sharply to 1 gram per cubic centimeter. Again, solid iron has a density of 7.8 grams per cubic centimeter, but this decreases sharply when iron is melted to the liquid form, which has a density of only 6.9 grams per cubic centimeter. An atomist might point out that a ready explanation for this is that in one state, the constituent atoms are more compact than in the other. Usually, it is the solid state which is denser, with water a rather unusual exception. However, in all such changes, the density varies by only a few %, and this is not overwhelmingly convincing. Working against the atomist is the fact that liquids and solids are relatively incompressible. Large increases of pressure, attainable only with specialized equipment, are required to bring about even small decreases in volume. For this reason, there can't be much empty space in ordinary matter, and every atomist must admit that in liquids and solids, atoms, if they exist, are in virtual contact. Since liquids and solids remain incompressible at any temperature, the feeling that atoms are further apart in hot water than in cold, or in liquid iron than in solid iron, seems to be wrong. If it were not wrong, then hot water and liquid iron would be at least moderately compressible, and they are not. It is another matter entirely, however, when the point of view shifts from solids and liquids to gases. When liquid water is boiled and gaseous steam is formed, the change in density is drastic and dramatic. Where water has a density of 0.96 grams per cubic centimeter at the boiling point, steam at the same temperature has a density of no more than 0.0006 grams per cubic centimeter. Steam is only about 1/17,000th as dense as water. This can be reasonably explained by adopting an atomistic view. One can suppose that the constituent atoms, or groups of atoms, making up water, move far apart in the conversion of the liquid water to the gaseous steam, and that steam is as low in density as it is, because it consists mostly of the empty space between atoms. We might generalize and say that whereas in liquids and solids atoms are virtually in contact, in gases they are far apart. This spreading out of atomic particles would account not only for the extremely low density of gases, but also for their low pressure, their small frictional forces, and so on. If this atomistic view is so, and if the particles of gas are widely spread out, then gases ought to be easily compressible. If pressure is exerted upon a given volume of gas, that volume ought to decrease considerably. This is actually so, and the fact was first clearly presented to the scientific community by the English physicist Robert Boyle, 1627 to 1691, in 1660. He poured mercury into the open long end of a J-shaped tube and trapped some of the air in the closed short end. By adding additional mercury, he raised the pressure of the trapped air by an amount he could measure through the difference between the inches of mercury in the open and closed sides. He found that doubling the pressure of the trapped gas generally halved its volume. Tripling the pressure reduced the volume to a third, and so on. The trapped gas was always able to support the column of mercury on the other side once its volume had been reduced by the appropriate amount, so that the pressure it exerted was equal to the pressure exerted upon it. This is to be expected from Newton's third law, which, however, was not yet enunciated in Boyle's time. Consequently, we can say that for a given quantity of gas, the pressure, capital P, is inversely related to the volume, capital V. So, as one goes up, the other goes down. Capital P is equal to lowercase k divided by uppercase V. Therefore, the product of the two remains constant. P times V equals K. Equation 10-1. This relationship is called Boyle's law. Another way of stating Boyle's law is as follows. Suppose that you have a sample of gas with a pressure, P1, and a volume, V1. If you change the pressure, either increasing it or decreasing it, to P2, you will find that the volume automatically changes to V2. However, the product of pressure and volume must remain constant by equation 10-1, so we can say that for a given quantity of gas, P1 times V1 equals P2 times V2, equation 10-2. And that, too, is an expression of Boyle's law. Indeed, gas is so easily compressed that the pressure of the upper layers of a column of gas will compress to lower layers, whereas a column of virtually incompressible liquid has a constant density throughout. Columns of gases vary considerably in density with height. This is particularly noticeable in the case of the atmosphere itself. If gas were as incompressible as liquid, and if it were as dense at all heights as it is at sea level, then one could easily calculate what the height of the atmosphere ought to be. Air pressure is 1,033.2 grams of weight per square centimeter. This means that a column of gas 1 square centimeter in cross-section and extending straight upward to the top of the atmosphere weighs 1,033.2 grams. A column with such a cross-section, but only 1 centimeter high, has a weight of 1.3 milligrams. Each additional height of 1 centimeter added to the column would add an additional 1.3 milligrams, and it would take a total height of about 8,000 centimeters to account for the 1,033.2 grams of air pressure. This is a height of just about 5 miles. However, this cannot be right, for balloons have found air to exist at heights of over 20 miles, and less direct methods of measurement have shown perceptible quantities of air to exist at heights of over 100 miles. The point is that the atmosphere is not at constant density. As one moves upward, one finds that a given quantity of gas is under less pressure because the quantity of air above it has become less. By Boyle's law, that given quantity of gas must therefore take up a larger volume. Consequently, as one rises, the amount of atmosphere remaining above, while decreasing rapidly in weight, decreases only very slowly in volume. For that reason, indeed, the atmosphere has no definite upper edge, but fades slowly off for hundreds of miles above Earth's surface, decreasing in density until it peters out into the incredibly thin wisps of gas that make up the interplanetary space. By pointing out the atomistic argument first, I was trying to make absolutely clear the importance and significance of Boyle's experiment. It is not to be supposed, however, that one experiment at once turned scientific opinion toward atomism. It was not until the first decades of the 19th century, a century and a half after Boyle's experiment, that the weight of evidence had finally accumulated to the point where scientists could no longer avoid accepting atomism. The scientist usually given credit for the final establishment of atomism is the English chemist John Dalton, 1776 to 1844. He worked out the modern atomic theory in detail between 1803 and 1808, basing it chiefly on the observations of the properties of gases that had begun with Boyle's experiments. In fact, one might maintain that Boyle's law made atomism inevitable, and that all that followed merely served to place a finer edge on the concept. It is now generally accepted that all matter consists of atoms, and that these atoms may exist singly, but much more commonly exist in groups of from 2 to many hundreds of thousands, and that these groups of atoms, called molecules, maintain their identity under ordinary circumstances, and form the particles of matter. It was by considering gases to consist of a collection of widely spaced molecules, or occasionally of widely spaced individual atoms, that it became possible to view such phenomena as sound and heat in a new and more fundamental manner.